Welcome to homework.
In this problem, we need to make a multiple choice question about the difference between the quantum world and the classical world. And in order to construct this question, I'm going to first review the correspondence principle. So remember that we have a very good theory that explains the quantum world, that's quantum mechanics, and we also have a very good theory that explains the classical world, which is classical mechanics. The quantum theory usually explains very well very small objects and objects that have very small energy. So small energies. Classical world, classical theory actually, explains everyday objects. Everyday objects. Okay. And initially, these two theories, they seem to be completely separated from each other. But what the correspondence principle tells us is that quantum theory, if we really expect quantum theory to be more fundamental, must explain not only very small things, but everything. So in some limit, quantum theory must correspond to classical theory. This means that in the limit where we take our objects to be very big, to be very energetic, so if we take our objects to be very energetic, and also they are in a coherent state, then quantum theory must correspond to classical theory. This means that quantum theory is more fundamental than classical theory, and classical theory is more of an approximation of quantum theory. Now we can go on to the exercise, and I've already wrote it right here. So the exercise that I wrote is this. Select the correct answer. And what I'm going to do is to evaluate one by one the four alternatives that I have here and choose the one that is correct. And I will explain to you why some alternatives are wrong. So first, A. Quantum mechanics is a fundamentally limited theory since it fails to explain the classical world. We know that this is not true. Okay, just as I explained before, we expect quantum theory to explain the classical world in a certain limit. Of course, it may not be very productive or practical to apply quantum theory when you're talking about just throwing a ball and letting it free fall according to gravity. But nevertheless, we expect quantum theory to explain these everyday situations. So this is wrong. Then B, photons are inherently quantum particles. Therefore, there are no limit in which photons can be satisfactorily described by classical theory. This is not true. We know that photons, if we have many photons that are very energetic, we can expect them to behave in a classical way. So, for example, classical electrodynamics explains optics very well, and optics is basically made of photons. So it's the study of photons in a classical manner. Of course, we don't talk about these quantum particles there, but if you make an experiment, you see that the results that you have are compatible with the prediction of classical optics. So photons in a certain limit can be explained satisfactorily by a classical theory. Then we have question C that says that in the appropriate limit, that is of large energies in coherent states, quantum mechanics must be well approximated by classical mechanics. And this is true. This is exactly what I said before about the correspondence principle. Okay, so I'm gonna mark this alternative. Then let's see why D is wrong. Electrons cannot be described by classical physics because they always behave as waves, while classical physics requires that they be treated as particles. That is not true. They don't always behave as waves. Okay, they behave as waves sometimes, and they behave as particles sometimes. The truth is that quantum mechanics allows particles to be both, uh, to act both as waves and particles. So this is wrong. And this concludes our exercise.